Okay, so this is our first rational function that we get to graph. And we're going to start and go through all of them. So the first one, the degrees are the same. And then we'll do one with the degree at the bottom is bigger. And then one with the degree at the top is the bigger. So we'll go through all three different horizontal asymptotes. So on this one, it's the same. So we already know that our horizontal asymptote will be our A over B. And we'll get to that when we get to it. Okay, so the first thing you're supposed to always do is factor these. And so I factor out a common x and then factor the trinomial. And what you want to do now is look for things that cancel. So on this one, our x's cancel. And so that gives us x plus 3, x minus 5, and x plus 1. And so now this is the one we use. We use this, but we have to stipulate a condition here. That x was still a denominator, which means that x cannot equal 0. So we say x cannot be 0 here. Because if that was 0, this whole thing would come out to be undefined. And so what that means is we now have a hole. And that hole is at 0, comma, and then there's a y value. So what you want to write now is you just change the function. We call it g of x. Or y equals, let's just use y equals. Y equals x plus 3, x minus 5, x minus 4, x plus 1. This is now the one that we're going to use for all of our questions. So when it says find intercepts, find y-intercepts, we look here, not here. We've simplified our function. But we have to make sure we include the whole. So now if I were to take 0 and plug it in up here, I would get 3, negative 5, negative 4, and negative 1. Move that up a bit. Okay, so simplifying that would give me negative, and then it would be 15 over 4. And so that is our point. And if we plug that in our calculator, we get negative 3.75. So now we're going to go down to our graph at the bottom and plot that. So it was at 0 and negative 3.75. And you don't want to put a dot. What we're going to do is grab the red marker and we're going to put a hole. Right there is our hole. So our graph will go through that point. However, it's not an actual point on the graph. All right, so that's how you deal with holes. So anytime something cancels, like this in our rational function from the top and bottom polynomial, we set them equal to 0. Tells us where our hole is going to be. Plugging it into the simplified function will tell us exactly where the hole is. Okay, now what we need to do is find the x-intercepts. And so we take our numerator, the x plus 3, and the x minus 5, and we set those equal to 0. So this tells us we have an x-intercept at negative 3, and another x-intercept at 5. So what that means is if I were to plug in negative 3 into my function, this whole thing would come out to be 0. And if I plug in 5 into my function, the whole thing would come out to be 0. So we have the point negative 3 comma 0 and the point 5 comma 0. So now we can go down to our graph and plot those. So at negative 3, 0 and 5, 0, we have our 2 points now on our graph for x-intercepts. Now the next one we want to do is find the y-intercept. And the y-intercept is very quick. All it means is x is equal to 0. So if we take our function and we plug in 0, what we end up getting is negative 15 over 4. Why can't we plug in 0 in this situation? So we can't plug it in for this function. It's fine for other functions. You always want to try, but why can't we do it here? Because it's our hole. 0 was already told to be an undefined value, so there is no y-intercept. So you can't put it down there. Intercept. All that means is that when you graph this, you can't graph a point on the y-axis, isn't because there's a hole. There it is right there. So our function will go through it as if there was a y-intercept. There just isn't. So we now move on to vertical. And remember, vertical is our denominators. So if you notice, all we're doing is taking every single piece of this function and applying it. So the top is giving us the x-intercepts. The bottom is giving us our undefined values, which is our vertical asymptotes. The leading coefficients is giving us the y. We factored it to find the whole. So we're dissecting this entire rational expression by its polynomials. I already forgot what the denominator was. X plus 1. So remember, using this, we use the bottom bad, and we say x equals 4 and x equals negative 1. And let's change this to red so that they match. There we go, and let's put them on the graph. So 1 at 4, we put a vertical dotted line, and 1 at negative 1. So that's why I'm doing red is bad. Your function will never have an x value at that point. So if you were looking for a domain here, our domain goes from negative infinity to negative 1, from negative 1 to 0, from 0 to 4, and from 4 to infinity. So that is our domain. It's all of those values for the bottom. So we know that x cannot be 0, 4, and negative 1. So putting them in order, it'd be negative infinity to negative 1, union, negative 1 to 0, union, 1 to 4, union, and then 4 to infinity. So we have our x can't be negative 1. Our x cannot be, see, I wrote it wrong, 0. Cannot be 0. Oh, it is 1. Negative 1 to 0. And then 0 to 4. Sorry about that. X can't be 0. And then x cannot be 4. So those were the three that we had. Can't be here, can't be here, can't be there. That's our domain. And so that's what we're graphing here in red. So now all we need is our horizontal. And if you remember the horizontal, if the degrees on the top and bottom are the same, it's the leading coefficients. So we know this is 1 and 1. So that means we're going to get y equals 1 over 1, which is 1. So y equals 1. If you need a reminder on that, you can watch the video on horizontal. So now we go to 1. And we've got our nice graph here already done. So you can already see that this one is here, that we have a graph here, right down here, because it's going to approach this asymptote and approach this asymptote. And then here we've got this one here and here, and then we're going to have another one that goes through here. So it could come up and then go that way, or come up and then go back down. So how do you find the points the quickest way? That's right, you plug it in your calculator. So pull out your TI 85 or 84 or Desmos, your choice, and we're going to graph this. So to graph these functions, you want to use alpha and y, and what it'll do is bring up fractions here. So if you select number 1, it'll put a fraction there. And now we can enter in our rational function. So x cubed, scroll out, minus 2x squared, minus 15x. And I'm plugging in the original because we want to make sure that what we canceled was a whole. So we want a full picture of it. And I'm going to show you how that looks. 3x squared minus 4x. And then you're going to hit zoom and 6. And you'll get our graph. So there was the first part, remember? And then we had a vertical asymptote here, a vertical asymptote here. And you can see there is our whole. And see, this is another benefit to using the calculator. Our whole is supposed to be positive, not negative. It is a simple error that you will make, because I did, so of course you can make it. And you probably already saw that and said, oh, it's supposed to be positive 1, Mr. McCants. You need to go back and change that, and I just did. So now you don't have to comment and say it's wrong. So we can come down here, select the red, and then we put it at the 3.75 up here. But that's the nice thing. So you see, this is why we want to input the entire function in, because then it'll show us the whole. And then now all we're going to do is transfer this onto our graph, because we just need a nice rough sketch. But when you do this, don't do this, because number 1, it doesn't cross the asymptotes. These are approaching it. So you want to be nice with it when you're graphing it. And then just do like a sketching motion down. Like that. And then a sketching motion this way. See, you're approaching these asymptotes. That's the key. You approach them. And if you want some values to see how low it goes, you can sit there and use the trace function. We can do a min here if we wanted to. We can go second, calc, and then minimum. And then we know it's between 1 and 3. So we do 1, enter, 3, enter, enter. And it says it's going to go down to 2.49. So you could come down and go, okay, well, it's going to be at 2.49. What was the x coordinate? Completely missed that. 1.8. So at 1.8, it's 2.49 right here. And so you can get a little more precise graph if you want. Just make sure your asymptotes are approaching like that. So that's why you notice I'm just doing a sketching motion as I graph it. Don't try to draw it fast. And see, I went over a little bit there. And there you go. There is your graph. And we can even verify that that is an undefined value. So if you hit trace and 0, you'll see it says undefined. Well, how do you verify that that is 3.75? Well, you go back to y equals, you scroll down, and you enter in the other function. So that is the alpha y parenthesis x plus 3 x minus 5, the simplified factored form. That's what you want to put in there. X minus 4, and then x plus 1, close it, hit graph, and you'll see that the red now will just trace it because they're exactly the same function. The only difference here is there was a hole with the blue. So now when I hit trace and 0, it says 0, right? But if I scroll up, it now tells me exactly what number it is, 15/4. So scroll down, it's 0, undefined, 15/4. So it shows me that I am correct, that it's 15/4 for my 0. And that is how you graph rational functions where the degrees are the same, top and bottom. So you should have that for your graph. You can also use the table if you wanted. I probably should show you that. So second table, and there are some actual values in there. So you can see that there's an error at 0 and an error at 4, but it shows up here. So you can, see there's the -1 as well. Go back and pick any of these points and plot them. Doesn't matter if you pick red or blue, you're just going to plot any of these points on the graph to get a little bit more precise picture. All right, thank you.